So is right. And she's an assistant professor in Canada in the Department of Computer Science and Operations Research in the University of Montreal. She very recently completed her PhD just last year in 2023 in Industrial Engineering and Management Science at the Northwestern University. And previously, she got her undergrad degree in mathematics at the Carleton College in 2018. In general, she develops a theory and algorithms for mixed integer nonlinear programming, and she applies it to complex models with real-world applications. But today, she will be talking to us about diminishing returns submodular functions. Please go ahead.
Thanks a lot for inviting me and for the kind introduction, Sylvia. I'm really excited to be here today and to share with you about minimizing a class of nonlinear functions over some mixed integer variables subject to some constraints. And this is a joint work with my PhD advisor, Simke Kuchikiewicz, at Northwestern University. So as this title suggests, we will be exploring the so-called DR-submodular functions. Let me first explain what that means and why they're useful. Here, DR stands for diminishing returns, which just means the decrease in marginal output. To illustrate this phenomenon, let's consider the problem context of sensor placement. Suppose these drawings, these little drawings are sensors, and the circles around them are the corresponding coverages. We use the solid blue regions to capture the coverage corresponding to the sensors that we have already installed. So they're currently in use. And the orange striped regions represent the respective marginal contribution if we were to add an additional sensor in location I. What we observe is that the more sensors that we have already installed, the less additional benefit we gain by adding another one. So in short, the marginal contribution of additional sensors diminishes. That's where the diminishing returns phenomenon shows up. And I should highlight that a DR is a ubiquitous phenomenon in real world. It occurs in all applications that involve clustering, coverage, economies of scale, risk aversion, etc. So by which what I'm trying to say is that the functions that are able to capture this phenomenon has a great modeling power in practice, and this is why we care about them. And DR, or diminishing returns submodular functions, is one such class. Let me formally introduce the definition. I'll be using this E superscript I to denote a vector with 1 in the ith entry and 0 everywhere else. We consider any function f whose domain is in Zn across Rn. In other words, it takes in arguments with some general integer variables and some purely continuous entries. Purely integer or purely continuous ones, they work fine too. Now, before going into the detail of this inequality, let's set forth more notation. Here, I is any index of these dimensions, and we consider arbitrary pair of points x and y in the domain, such that x is component-wise smaller than y. And alpha is a non-negative parameter, such that if we augment by magnitude of alpha in the ith dimension to both x and y, we're still safely sitting within our domain. All right, so let's look at this inequality. The left-hand side is the marginal contribution of an increment in the ith dimension of magnitude alpha to x. And this marginal contribution dominates the marginal contribution if we were to make the same increment to this component-wise larger point y. So hopefully you can see some diminishing returns going on here. Essentially, the gist is the more that we have, so component-wise bigger, the less additional benefit we gain, or the lower the marginal return is if we were to add something additional to it. This is where the DR arises. Here is a picture of a univariate DR-submodular function, and the domain is over general integers. If we consider this pair of points, x and y, and let alpha be 3, then the length of this blue bar represents the marginal contribution, so this term. And the negative of the length of this dashed line segment corresponds to this, the right-hand side. So again, this is just an example to illustrate that this inequality does hold. Now, if you look at this picture, you may be wondering, oh, does it mean that DR-submodularity is just some discrete analog of concavity? What I should highlight is that DR-submodular functions are a lot more wild than that. They're not necessarily concave. For example, quadratic functions with non-positive Hessian entries are DR-submodular. And these functions can be nonconvex and nonconcave, just like this one in the figure. And if we consider the domain, restrict the domain to be just the binary lattice, then the well-known classical submodular set functions are a subclass of DR-submodular functions. Well, we have now seen that DR-submodular functions capture an important real-world phenomenon, and we can certainly model things with it. But to inform decisions, we do need to optimize such functions. And this is when big challenges may arise. Because, well, in general, these functions can display some wild nonlinearity. And on top of that, some problem contexts may even call for not just binary, but general integer, or even mixed general integer decision variables, which makes the corresponding optimization problems even more difficult. Well, before going on to how we may tackle those optimization problems, let me just share some examples. So we have this budget allocation in advertising, that's one. We can also handle influence propagation with varying incentives. That's another application. Last but not the least, the sensory energy management is also, we may observe this kind of optimization challenges. Since I've been talking about sensors earlier, let me just go a bit further in this last application. Suppose we'd like to monitor the water quality in a lake, and we can do so by deploying some sensors at certain locations. What's special about these sensors is that they have adjustable energy levels, and this is our decisions. Depending on the build, the models of these sensors, some of them can have discrete levels, and some of them can have continuous energy dials. So they are naturally represented by continuous and discrete variables. It's known that the function capturing the expected reduction in pollution event detection time is DR-submodular. And I'm just including the form of the function here to showcase it is highly nonlinear, but don't worry about the details. And I'd like to highlight that we may be, so these energies are naturally box constrained. There's upper bound and it should be non-negative. And on top of that, we may want to consider other constraints. For example, we may care about information in certain locations more than some others. So we would naturally want to give more energy to the sensors at these locations, which could be modeled by the so-called monotonicity constraints that I will explain further later. Okay, so at this point, hopefully I have motivated the study of this class of optimization problems. And let's see, methodology-wise, what's been done in the literature. The current literature predominantly focuses on the maximization direction, mostly approximation algorithms with provable guarantees over, well, the pure continuous, the pure integer domains, as well as the purely continuous spaces have been explored. And in contrast, relatively few studies have considered minimizing DR-submodular functions. And among the most relevant studies, these two works handled box-constrained integer variables, and the resulting algorithms rely on some sort of binary expansions. So the complexity is dependent on the variable upper bounds, well, coming from the box constraints. And concurrent with our work, Han et al. Tackled a related problem class that's, oh, no, go back, I'm sorry. All right, sorry. So they tackled a related problem class that's inspired by Markov random fields. They have mixed binary variables and have certain objective and constraint structures. And they showed that this problem class is polynomially solvable. To this end, we observed that there was still quite a lot of gaps to be bridged, including the following questions. Can we minimize any DR-submodular functions with continuous and or general integer variables? And can we handle constraints that's beyond the simple box constraints? And can we find the global optima despite all these additional challenges in polynomial time? That's what we were trying to explore. With these questions in mind, we took a polyhedral approach to this minimization problem under possibly additional monotonicity constraints, which I sort of motivated in the sensor application. And we allow mixed general integer variables. Specifically, we proposed new valid linear inequalities with which we managed to describe the epigraph convex hull completely. And we proposed an exact separation algorithm for these new valid inequalities. Combining all these results, we were the first to establish the polynomial-time solvability of this class of constrained, mixed integer, nonlinear minimization problems. Before delving into the technical details, I want to highlight the key takeaway is that surprisingly, the convex hull of the epigraph of any DR-submodular function, imagine this is not just purely continuous and box constraint, it can be mixed integer with additional constraints. The convex hull is polyhedral. So what this means is that this seemingly difficult mixed integer constrained nonlinear problem is nothing but a simple LP. We were pleasantly surprised by this. All right, so now let me formally state our problem and get into the technical details. We minimize any DR submodular function f over a set called ZGU. And as promised, well, this is our refusible set. As promised, our decision variables z are indeed mixed integer. We allow that. They are box constrained, which is consistent with the literature. And we include possibly additional monotonicity constraints. And let me explain where these constraints are governed, how they're entered into the model. So V is this index set for all the dimensions. And G is the digraph with vertices V and some arc set A. And this arc set A governs the monotonicity constraints. Every arc ij in A gives us a monotonicity constraint Zi less than or equal to Zj. Now let's zoom in onto the part that concerns the monotonicity constraints. In particular, the G's are directed rooted forests. By that I mean G is a disjoint union of directed rooted trees. Well, the tree structure is desirable because it avoids the cycles that can imply equalities. So that's redundant information. And this example A is a directed rooted forest with 3 disjoint components. This is a directed rooted tree because, well, it has a root, the hexagon. And if these are just edges, it's clearly a tree. And it's directed because all the arcs have directions and they're pointing away from the roots. Well, this one in the middle is also a directed rooted tree, even though it does not have any arcs. And if we look at this arc, it just means that Z8 is less than or equal to Z9 in our model. And on the right, this example B is also a valid directed rooted forest. And the corresponding feasible set is just box constraint because we do not have any arcs, so we do not have any additional monotonicity constraints. What I'm trying to say is that this generalizes what's been studied or considered in the literature. Okay, now we can reformulate this original problem using its epigraph P to the ZGU sub F And we introduce this epigraph variable w to capture everything above the function value over the feasible mixed integer points. And now our task is to understand the convex hull of this mixed integer set the best we can. We quickly noticed that convexifying, not for the epigraph, but just for the mixed integer feasible set is already non-trivial. This is because the continuous relaxation of our constrained mixed integer feasible set, it's not necessarily its convex hull. So here is one example. It's a pretty generic directed rooted forest with one component. The squares represent the discrete decision variables, and without loss of generality, we can assume they're upper bounded by integer parameters. And these circles represent the fractional, the continuous decision variables. Some of them may be upper bounded by integer parameters, and these striped ones, the other ones, are upper bounded by non-integer parameters. We observed that certain pairs of these variables cause troubles. So in this example, we zoom in, let's zoom in onto the dimension Z7 and Z8. Given this arc, we have the monotonicity constraint, Z7 less than or equal to Z8. And Z7 is a continuous variable, upper bounded by a fractional number, let's say it's 2.4. And Z8 is an integer variable, let's say it's upper bounded by 3. Then the dot and the bars are the feasible points under the integrality restriction. This dotted region is the continuous relaxation given the constraints. But what we really wanted is this convex hull, the purple region. Unfortunately, we observed that there is this extra triangle that we need to cut off. After some hard work, we found out that the mixed integer rounding inequalities will handle this. So this is a linear inequality involving Z7 and Z8. And pictorially, this is what this mixed integer rounding inequality does. In general, we managed to characterize the troublesome variables, just like Z7 and Z8. We throw them into this set called capital psi. And essentially, these are the fractionally upper bounded continuous variables with discrete descendants. That's the ones that's causing troubles. And again, with some hard work, we managed to show that to describe the convex hull of the constrained mixed integer feasible sets, we just need the trivial inequalities and the additional mixed integer rounding inequalities for all these troublesome variables and their children. And I should highlight that these are just linear inequalities. These are the parameters that's pretty easy to compute. All right. Now we face the second big challenge, which is to characterize the convex hull of the epigraph, not just the feasible region, but now one dimension up with the epigraph dimension. We proposed what we call the DR inequality. Each DR inequality is associated with a delta, which is a permutation of all the indices. So as you can tell, there could be exponentially many of these. And again, with some hard work, we managed to show that these inequalities are indeed valid for the epigraph. And let me just try to give you some intuition about what these inequalities are doing. The right-hand side involves some function evaluations at some interesting points. What are these points exactly, you may ask? Well, suppose we're dealing with a three-dimensional problem, and one delta, a permutation could be 1, 3, 2, with which we can construct a sequence of nested subset of the index set. So we start from the empty set, and then we add the first item and the permutation to get T delta 1, and add the second one to get T delta 2, etc., until we recover the full index set. And each such subset corresponds to an extreme point of the convex hull of the feasible set, which we just characterized. So for example, this empty set is mapped to this extreme point, and this singleton is mapped to this extreme point. I'll omit all the technical details, but I just want to highlight that we know exactly what P is, and we know how to write that out explicitly. And then now let's look at this part in our proposed inequalities. Well, the function t are given as follows. Again, don't worry about the details. By showing this, I just want to highlight two things. If we fix any delta, t delta z, it's just a linear expression involving our decision variable z. It's linear. And we know exactly how to explicitly write that out. So in essence, the right-hand side of each DR inequality is just a sum of linear expressions of our decision variable z, weighted by some function evaluations. And these are just numbers. So they are linear and, well, they are also homogeneous. Now, by combining all these inequalities that we've discussed, the trivial inequalities, the MIR inequalities, and these new DR inequalities, we managed to completely represent the convex hull of the epigraph. And the immediate implication is that, well, the convex hull of the epigraph of the nonlinear DR-submodular objective over some constrained mixed integer set is fully described using linear constraints, meaning that we can convert the seemingly hard problem into a purely continuous linear program. Now, the only thing that we need to worry about is, again, because there are exponentially many permutations, we have exponentially many DR inequalities. So it's exponentially sized, and we don't like that. But in the cutting plane, well, in the delayed constraint generation framework, we can easily handle that as long as we can efficiently separate these inequalities. And we managed to come up with an exact separation algorithm. We can find the most validated DR inequality at any infeasible fractional point. And this algorithm is essentially some generalized greedy algorithm. So it does this cardinality V rounds of sorting. So this runs in polynomial time. And this complexity is only dependent on the dimension of the problem and has nothing to do with the parameters and the constraints, like the box constraints upper bounds. And well, due to the equivalence between optimization and separation in linear programming, we conclude that this class of constrained mixed integer nonlinear minimization problems is actually polynomial time solvable. All right, so at this point, we have successfully addressed all of these research questions. Well, yes, we can minimize any DR-submodular functions with a mixture of continuous and general integer variables. And this includes pure continuous and pure integer cases as just special cases. And we can go beyond the box constraints and tackle additional, well, they're not mandatory, optional, monotonicity constraints. Oh, and well, the whole problem can be exactly solved in polynomial time. And yeah, with this concludes my presentation, and I'll take any questions. Thank you.
Thank you for the nice talk. Are there any questions from the audience? Please write them in the chat or just.
Yes, I have one. Thank you, Kim, for the great talk. Relevant to the polynomial time guarantee. So what I know is that for submodular set functions, there's this famous approach, I don't know, n to the power 6 polynomial algorithm. So I was just wondering about the complexity in this more general case relative to the set function case.
Relative to the set function case. Well, so I should say that, well, to the best of our knowledge, we're the first people to establish the polynomial time solvability of this problem class. So there is no methods that's parallel to the method that you were mentioning for the submodular set functions. But it certainly gives us hope that it can be done. And I have the intuition that given how much our polyhedral results generalizes the classical submodular set function minimization, I can see potential in generalizing those proposed methods for submodular set function minimization over ring families. That's one type of constraint structures that's been looked at in the literature. And I can see that some progress can be made in that direction. Yeah, thanks.
Okay,
hopefully
great,
that
thank you.
addresses the
Yes,
question.
yes, it does, yes.
Any other questions? Okay. So I have one. Could you give me like a quick overview of how the separation algorithm works? Like, is there a combinatorial algorithm or idea behind it on how you actually find the most violated one?
Yeah. So we can start with the classical submodular set function. Well, this classical notion of submodularity, and there's this famous greedy algorithm that exactly solves minimizing linear objective functions over extended polymatroids.
Yeah.
So what you do is you solve some sort of relaxation with partially many, well, a subclass of DR-submodular inequalities that works for just the classical submodular set functions. You get some fractional solution, which is infeasible. Then you just sort the fractional entries of Z, which gives you a permutation. And once you obtain this permutation, you know which additional valid inequality to feed in. So what's been extended here is that it's no longer just one round of sorting. We do need to do the cardinality V rounds of sorting. So if it's a three-dimensional problem, we do 3 rounds of sorting to give us a permutation, which then helps us identify the most DR, a violated DR inequality.
Got it.
Yeah.
Thanks.
Thank you.
If anyone has other questions, you can join Kim after the end of Madeline talk in the breakout room. And in the meantime, then we can move on to the second talk. Elias, I leave it to you.